Apache Beam is a framework for writing data processing pipelines which can be ran in parallel. It allows you to define both batch and stream pipelines and is compatible with many of the most popular frameworks for distributed processing, such as Apache Flink, Apache Spark, or Google's Dataflow, which is a cloud service for hosting Apache Beam projects. These different compute options are called runners within Apache Beam, and for development we can also use our local compute as a runner. Today we're going to leverage Apache Beam to run several data processing pipelines in parallel in a way that can easily be deployed to the cloud later on. To demonstrate this, we're going to transcribe audio from news bulletins. Each of these news bulletins has an RSS feed, which is where we'll be getting the data from. We'll then parse the RSS feed and return a dictionary, retrieve the URL of the audio and download that as an MP3, and then finally transcribe the audio and save that as text. We'd then like to run this pipeline several times so that we can extract information from several news sources, and we can run each of these pipelines in parallel using Apache Beam. So let's start by creating a new folder for our Python project. Now we've created a new folder and navigated into it, let's create a new virtual environment. And now let's activate the virtual environment. Now I'm going to open my code editor from this directory. Next, make a source directory to store our scripts, a podcasts directory to store our audio, and a transcriptions directory to store our text. Let's also create a modules directory inside the source folder and an init file inside the modules folder. We're going to create 3 class types in this project. One will be feed, which can be parsed, another will be episode, and another will be the pre-trained models we're going to use for transcription. So let's create a feed script in our modules directory. Let's create our feed class, which will be initialized with a name, the URL of that RSS feed. I'll be adding print statements like this throughout the video. Then we set the name and the URL to the feed name and feed URL respectively. Next, we're going to define a method for retrieving the latest episode from a feed. Pip install feed parser, as we'll be using this to translate the RSS feed into a dictionary, and import feed parser into the feed script. Then use the parse function from the feed parser module to convert the RSS feed URL into a dictionary. The dictionary containing the data for the latest episode will be the first element in the entries list. From this latest episode dictionary, we can access the title using the title key. Next, pip install the datetime module and import it into our script, as well as importing the time module, as together they can be used to parse the datetime found in our latest episode dictionary. Now we've got the title and the datetime of the episode, the next thing we need is the episode URL so that we can download the MP3. This can be found at the href key of the first element of the enclosures list in the latest episode dictionary. Now we have all the information we need, we'd like to be able to make an episode class. However, that needs to be defined in a different script called episode.py. Therefore, we're going to make an episode.py file to define that in. Let's create a new class called episode and initialize that with a channel name, an episode name, a URL, and a release date time. Set the channel name to be the channel name, the episode name to be the episode name, the full name of the episode to be a combination of the channel, the episode title, and the release date, the URL to be the URL, the release date time to the release date time, and the safe channel name to be each letter in the channel name string with all non-alphanumeric characters replaced with an underscore, and the safe episode name to be defined similarly, except with the release date time prefixed. Now we can initialize an episode object, go back to the feed script, import the episode class, and define the latest episode by passing the name, the title, the URL, and the date time to the episode class. Then return the latest episode, and add the expected return type episode to the getLatestEpisode function. Now we have a way of retrieving the latest episode from a feed. The next thing we want to be able to do is download an episode. So we create a download episode method on the episode class. We define the directory we want each episode to be saved into, using the channel name so that episodes from different RSS feeds will be saved under different paths. Next, import OS and use the make directories function to create this directory even if it already exists. Next, we define the name of the file as the safe filename.mp3, and then we define the file path by concatenating the save directory with the file name. Next, we import the requests module and use it to get a response from the episode URL, setting stream equals to true, which prevents the whole episode being loaded into memory. Then we open our file path with the ability to write binary, and then break the file into chunks of 1024 bytes and write each chunk to the path. This is all we need to download an episode. The next thing we'd like to do is transcribe an episode. But to do this, we'd need a pre-trained model which we'll call a transcriber. This will be a class of its own. Therefore, we'll make a models file in our modules folder, which is where we'll define our transcriber class. The model we're going to be using is Whisper from OpenAI, which is a pre-trained model used for converting audio to text. We're going to be using the tiny version as inference will be run locally for this video. Therefore, we will pass a parameter model size to the initialization of the transcriber class and insert this into the model name so that it matches the name of the repository on Hugging Face. To download and use this model, we need to install Hugging Face's transformers module. We do this with pip install transformers. From the transformers module, import the Whisper processor, which we'll be using to process our data, and the Whisper for conditional generation class, which we'll be using for inference. Then set the processor of our transcriber to the Whisper processor configured to our specific model by passing our model name to the from pre-trained method, and set the model of our transcriber to Whisper for conditional generation configured to our specific model by passing the model name to the from pre-trained method. Now we've defined how to initialize our transcriber, go back to the episode.py file and from modules.models import the transcriber class. Then go back to the transcribe episode method we were defining earlier and set the expected type of our transcriber parameter to the transcriber class. The first thing we want our transcribe episode method to do is ensure the episode is downloaded by running the download episode method. Next, define the save directory using the transcriptions path with the save channel name. Next, use the make directories method from OS to ensure that our save directory exists. To prevent us loading entire episodes into memory, we want to break each episode down into 30-second chunks. Therefore, we set our chunk size equal to 30. Next, we set the sampling rate to 16,000. This determines how many times the audio is sampled per second. We define the path to our MP3 file. To continue, there's some information we need to find out about our audio file. To break our audio file into 30-second chunks, we need to know the length of the audio file in total. To do this, we can use a Python module called Librosa. So next, pip install Librosa and import Librosa once that's installed. Then pass the file path of our MP3 to Librosa's load method. This will return the audio as well as the sampling rate. We can then pass the audio to Librosa's getDuration method, which will give us the total duration of the audio in seconds. Next, we import the math module and use the seal method from math to set a time cap in seconds. This takes the total duration and rounds it up to the next second. And then we set transcription to an empty string, which we can use to append on the transcription of each chunk as we iterate over the audio file. Now it's time to iterate over the length of the audio file in chunks of 30 seconds. This print statement will print out the progress of our transcriptions as we iterate over the audio file. For the start time of each chunk, we calculate the end time by adding 30 seconds to each start time. The end time of each chunk will be the start time plus 30 seconds or the time cap, depending on which is the smallest. Our audio is split into samples. Therefore, to take a 30-second slice, we multiply the start time and the end time by the sampling rate, which we then assign to the variable audio chunk. We then process our audio chunk with our transcriber's processor, ensuring that what is returned is compatible with a PyTorch model by setting return tensors equal to PT. Then we pass our processed audio chunk to the model to generate our token IDs. Then we pass our token IDs back to the processor and use the batch decode method to convert these token IDs into a string. This string will represent the transcription for this audio chunk. We then append the transcription for this audio chunk onto the transcription for the audio as a whole, and that's the end of our for loop. Next, we set the transcription file path using the save directory, the episode name, and .text. Then we open that file path with the option to write, and we write the transcription string to the .text file using the .strip method to ensure all leading and trailing white space has been removed. And finally, we add a useful print statement and return the transcript. Now we have all the components we need to build our audio transcription pipeline. We have a feed class with a parse method that creates an episode class with a download method that creates an MP3 file, and also a transcribe method that creates our .text file. However, if we want to run multiple pipelines in parallel, we need to use a tool like Apache Beam. So that's what we're going to do next. Let's make a main.py file where we can put these classes together in an Apache Beam pipeline. Next, use pip to install Apache Beam. Once you've done that, import the Apache Beam module and give it an alias Beam. Then import the feed class from our feed module, the transcriber class from our models module, and the episode class from our episode module. For Apache Beam to run a list of jobs in parallel, it needs to be given that list as a special type. That type is called a P collection. It's defined in the Apache Beam module and it stands for parallel collection. For our functions to be ran in parallel, for each element of a P collection, we need to define our functions as a special class called a do function. This is also a class from the Apache Beam module. For example, to create our initialize feed function, we set this to be a class which inherits the do function class from Apache Beam and the process method, which is what's executed at runtime. For this particular process, we want to pass a feed tuple, which we will define below. For now, all we need to know is that this can be unpacked into the feed name and feed URL. Then we create an instance of our feed class using the name and URL, and then use the keyword yield to return the feed after the process has been run. This means that feed can then be passed to the next function in our Apache Beam pipeline. Now we have a function to parse our feed, we need a function for getting the latest episode from that feed. Therefore, we define a class getLatestEpisode, which is also an Apache Beam do function. We then pass our feed to the process method of the getLatestEpisode class. Then we apply the getLatestEpisode method to our feed to return the episode. And finally, we yield the episode, as this is what we'll be passing on to the next function in our Apache Beam pipeline. The final function in our Apache Beam pipeline will transcribe the episode. So we'll call this class TranscribeEpisode. This time we also want to define the initialization method, as we want to pass this class a transcriber when it is created, not every single time the process method is ran, which will be multiple times in parallel in our Apache Beam pipeline. In our initialization, we set the transcriber to be equal to the transcriber we've passed. Next, we can move on to defining the process method, which has the episode as a parameter. We then pass the transcriber to the TranscribeEpisode method, which is applied to the episode and returns the transcription. And finally, we yield the transcription, as this is what we would like to be returned. Now that we've created our Apache Beam functions, we need to create a regular Python function which can piece these together. This function is going to be called runPipeline and will take an RSS feed dictionary as an argument. The RSS feed dictionary will be a list of RSS name and RSS URL pairs. First, we set the channel names to be the keys of this dictionary, and we use the string types join method to create a dynamic print statement of these channel names. We set the transcriber to use the tiny version of OpenAI's Whisper model. Now we're ready to start our Apache Beam pipeline. Within our pipeline, we're going to chain our transformations. Therefore, we start with the pipeline itself, and we always use the pipeline operator before our next transformation. Transformations can also start with strings that later on can provide useful logs. So that Apache Beam knows that this is a string intended to be a log, this is followed by double arrows and then our transformation itself. Here we're using Apache Beam's create to transform our dictionary into a P collection. Remember, a P collection is a parallel collection, which is a list that can be used to trigger jobs in parallel by Apache Beam. Once we have a P collection, the first transformation we want to do is initialize our feed by using Apache Beam's parallel do to call the initialize feed, which remember is an Apache Beam do function. We then want to follow this with the getLatestEpisode do function, the TranscribeEpisode do function, which we pass the transcriber to, and then finally we use Apache Beam's map function, which executes the print function on whatever is yielded at the end of TranscribeEpisode. In this case, TranscribeEpisode yields our transcription. We then end this by closing our brackets and add a print statement so that we know that this is complete. The intention here is that every transformation defined after our P collection will be ran once per item in the P collection and will be ran in parallel where possible. This depends on which runner you use for Apache Beam. For example, this is unlikely to run in parallel if I use my local machine as the runner, which I'm going to do for this video. However, if this was deployed to Google's Dataflow or was using Apache Spark, then it would be much more likely to run in parallel. Now that everything's in place, we're going to use the main guard to test our run pipeline function. First, I'm going to set a dictionary of RSS feed URLs that I've found on the internet. These are all RSS feeds of regular newscasts. You'll be able to find these in the GitHub repository for this project, which will be linked to in the show notes. Then let's call the run pipeline function, passing this URL dictionary to the function. Let's save the file. Use pip install torch to ensure that PyTorch is installed first, and then run the main.py file. We can see that this has started. We can see from the terminal that that's finished running, and we can see in the podcasts folder that the audio is downloaded, and in the transcriptions folder that the transcriptions have downloaded. Therefore, we've written an audio transcription pipeline in Apache Beam, which can run jobs in parallel and is portable. So if we ever wanted to deploy this to the cloud, we could do this without changing our code. If you found this useful or want to see more, then please like the video and subscribe to the channel. Thanks for watching.